And in principle, from now, everything is recorded. So let me just move that to the corner. If you don't see me do that at the beginning of the lecture, then just remind me, because otherwise I will forget. And then I'll try to post that, and we'll see if it works out. If it doesn't, then it doesn't. Okay, so we are still discussing potential flows. So those are, again, irrotational, incompressible flows. Right? So irrotational means that your flow derives from potential, so you can write the velocity field as the gradient of a potential function. And if you add on top of that the fact that the flow is incompressible, then that potential satisfies the Laplace equation. So there are many, many solutions that we have to the Laplace equation, so many tools that we have to express flow. So we discussed fundamental solution, uniform flow, source, sink, irrotational vortex, and dipoles. And then what we did is we used those little tools that we have that we can superpose to create the flow around the cylinder. By imposing the no-slip boundary condition on the no penetration boundary condition on the cylinder, and then we computed the drag force, and now we are computing the lift force. Okay, so remember the lift force is nothing but the total force which you get when you integrate over the entire surface of the cylinder the stress vector, which is the stress tensor times the normal vector, and you project it on the direction normal to the incoming flow. Okay, perpendicular to the direction of the incoming flow is the drag. Normal to the incoming flow, it's the lift. So that's what we are doing now. So I see little things moving here, so it looks like there is sound. So this is good, a good sign. Okay, so B, lift force. Okay. So let me just rewrite the integral. So our integral was integral over the closed contour, which is our cylinder. And again, it's a two-dimensional flow. Remember, we're only talking now about 2D planar flows. This is the only case where we can write all of our little singularity solutions. So integral from 0 to 2 pi of minus p on the normal vector, which is actually the radial vector in that case, because we have a cylinder. What happened? Let me just... Okay, times the normal vector, ds, which in that case is just r d theta. And now we are dotting, so we're projecting on the normal, on the direction perpendicular to the flow at infinity, and we took the flow at infinity in the x direction, so we're projecting onto the unit vector in the y direction. That's what we're doing now. And so when we integrate this, then we'll get our lift force. This is L. So this is equal to minus integral from 0 to 2 pi times the pressure. And remember, we are integrating on the surface of the cylinder. So we're not integrating over the entire bulk, of course not. We're just looking at the force on a particular surface, and that surface is determined by an equation, and in polar coordinate, this equation is r equals a. Right? We are at a distance on the surface of a cylinder. We are at a radial distance a from the origin. So the pressure is not pressure at r, it's pressure at r equals a, and all thetas. This is no longer working. Never mind. Theta, r d theta. Now r dot y, this is now equal to sine theta. Sine theta times r d theta, but r is equals to a, so it's a d theta. You know, last time we did the integral when this term here, the sine theta here, was a cosine theta. And so I'm not going to recompute this integral. I'll just give you the answer. You can do it for your own. You know, pressure. Remember how we got to pressure? We got to pressure through Bernoulli equation. Yeah, the steady version and the very strong version where the constant is independent on the streamline. And so what you would get if you computed that would be, let me just write it, integral from 0 to 2 pi of p infinity plus 1/2 rho capital U, which is the flow at infinity, minus gamma squared, which is the circulation, 4 pi a squared, times sine theta, A d theta. Right, so if you look at this first term here, you have a sine theta, which you integrate over 0 and between 0 and 2 pi. Yeah, the screen is really not great. Between 0 and 2 pi, so this gives you a 0. So this term here is going to be 0. Plus, we have a integral between 0 and 2 pi of 2 rho u squared sine cube theta A d theta. Now a sine squared will be a positive function. Sine cube is going to again oscillate between -1 and +1 over at least one period. In case for sine cube it will be over 3 periods. So when you integrate between 0 and 2 pi, this will also give you 0. So that term here is also going to be equal to 0. And then finally the last term plus integral between 0 and 2 pi of 1/2 2 rho, rho times 2 capital U sine squared theta gamma divided by pi A d theta. And this one, if you see, now this one has a sine squared, so this is always going to be positive. Right, so it's going to be positive between 0 and 2 pi. So the average value of this function over 0 to 2 pi is going to be 1/2. So you integrate, think about integrating 1/2 between 0 and 2 pi. It gives you 2 pi times 1/2. So the whole of the integration of that is going to give you 1 pi. So if you look at this, the pi is going to cancel out with this one, A cancel out with this one, 1/2 with this 2, and you're just left with rho u gamma. And this is your lift force, L, is equal, so this is going to be rho u times gamma, is equal to the density, so the lift force, times the velocity, the uniform velocity at infinity, times the circulation. Now this is absolutely fundamental in for air force theory. This is called the Joukowsky lift theorem. Depending on which country you did your undergraduate in, or you do your aeronautics in, or whatever, you have about 3 or 4 different spelling for Joukowsky. So I'm going to write it with a Z, Z-H-U, but you would find easily J-O-U, or you find all kinds of spelling. But this is called the Kuta-Joukowsky lift theorem. Now let me do a little reminder that just for that duration, and that's the only one where I will do that, I changed the sign for gamma, okay? And that is because in like the typical application for flow around the cylinder has to do with aeronautics. This is aerodynamics. This is really the solution that we are just computing here is the fundamental solution if you want to understand any, the origin of lift and all of the fields of aerodynamics. But in aerodynamics, what you have is that you have the flow around the cylinder. You will always count. So for some reason, the flow always comes from the left. Right? So the flow always comes from the left, and U is positive. And gamma in this direction here is positive. Right? And the reason why you take gamma in this direction, positive, is because it gives you a positive lift, and you want your lift to point upwards. Right? So note here that this positive gamma here is really the gamma in this direction. So in terms of how you would compute the integral, the circulation would really be minus gamma. We still call that gamma. Okay? Is that clear? So this is what you have. So if in this configuration you will have a positive lift force, and the lift force will be equal to rho u times gamma. Note that from this you see that you only have lift if you have a non-zero circulation. Right? If the circulation is equal to 0, there is no lift. Now that makes sense given also the general flow that we saw. if you don't put an irrotational vortex in the field, then the flow is symmetric, top down. You have the same thing on top and the same thing on down, so there is no chance of having more pressure on the bottom than you have on the top. Yeah. So let's see on MATLAB how this looks like. Okay, so let me go back to. Let me open this. So remember, here we are plotting all of the different fields. Let me just remind you of all the different fields. So this is our uniform flow. Kuhn, what is the shortcut for commenting out in Windows again? Control R for Control R. Okay. Control R. It's not working. So how do I comment now? Oh yeah, Control R. Okay. Okay. So this is the uniform flow. Right. So if you plot that uniform flow, this remember. Now you can do a uniform flow and add a dipole. So let me add a dipole here. So this is going to be the flow U1 V1. So then I have to just add the two up. So when you have a uniform flow plus a dipole, you have this flow here. Right. So now it's sorry, but it's hard to see on the screen. So I think it will be easier if I plot streamlines. So you can also plot the streamlines. And so if you plot the streamlines, then you see, so here I just put a dipole. So I have a uniform flow and a dipole. So those are the streamlines. Okay, so it's not optimal. But you see here your dipole. If you zoomed in on here, you would recognize your dipole with the source at the back and the source at the front. Or if you did the problem I suggested, the two irrotational vortexes with opposite circulation, which you bring together. And now you have your streamline, and so you see the flows on top and it flows on the bottom. Right? If you were to actually just deduce from the streamlines where the pressures are, right? You know that here you're going to have high pressure, here you have lower pressure here and higher pressure here, because those streamlines are deviated here. And it's the same here. You have lower pressure here and higher pressure here. But in the end, if you think about the streamline here, this is the surface of the cylinder, right? Then you have the same pressure on top and the bottom. So when you compute the net lift, there is no net lift. And you have the same depression on both sides, so there is no net lift. Now note, there's one thing which you could, if we are able to zoom in here, right, then we can see where the stagnation point is. So you see, perhaps you see those two arrows. There's one pointing this way and there's one pointing that way. So right here we have a stagnation point. Now note also that in general, here we have the flow around a cylinder, and we only really consider the flow outside of the cylinder. Whatever is happening inside the cylinder, we don't care. Right? So everything which is here, those streamlines, they don't represent flow. Right? If you had a bulky cylinder, inside of a cylinder you have metal, there is no flow. But the solution, you still have, the solution still gives you a flow inside, but it doesn't matter. There's no flow. You're only considering here, this surface here, and you look at the cylinder, you look at the flow outside. Likewise, actually, if you said, now I want to do something different, I want to see what would be the flow above a dip. Say you have wind that is flowing around a little hill. Well, you could take this line here, as this is a streamline here, so you could decide to disregard everything which is underneath and say this is now a solid, right? And if you think about everything which is on top of that streamline, it satisfies potential flow, so it's an inviscid, incompressible, it's an irrotational incompressible flow, right? Everything here. Along this streamline here, does it satisfy the low penetration boundary condition? Yes, right? And therefore you could say anything in there just models the flow on top of the little hill. You can pick any streamline and then just disregard the flow on one side, and whatever is left on the other side is an incompressible irrotational flow, where you satisfy the no penetration boundary condition at the surface. Right? So you can always do that. Okay, so this is not the point of our discussion. Now let's add the vortex. Right? So now we are adding a little vortex. Control the other one. Let me make it small at first. Right, so here is a vortex, and now you can barely see it, but I'm putting, so note that I'm putting a negative circulation, because my notations here are the standard notation, the real notation where gamma is positive in the positive direction. So if I want a lift to point upwards in the code, I actually have to put a negative circulation here. So -1 is too small, let's put -3. If I do -3, oh, sorry, I forgot to add the velocity field. I was wondering. Yeah, sorry, I forgot to add up the velocity fields. Now, if you add the velocity fields, then you see that. Okay, so you see that your streamlines are deviated a bit. Because you have this positive circulation here. Right? You're adding some positive velocity on top, so it rotates fast on top, and you're adding negative velocity because of the rotational vortex on the bottom. So the flow slows down on the bottom. Right? You see now you have that streamline coming in here, and if you really zoomed in there, you would see that your stagnation point, and we'll discuss that just in a second, but the stagnation point, so you know what, let me do it stronger so it will be more obvious. The stagnation point are moving down a bit, right? So the stagnation point is no longer here. It's actually right here. If you look, right? So I can see it sort of, but you can't. And my stagnation point is roughly here. Right? It's moved a bit it's still on the cylinder. It's moved a bit towards the bottom. Now, even if you didn't do the Kudai-Joukowski calculation, you would know that if this is an irrotational a potential flow, that there will be a positive lift. Why? Because if you think about the velocity here, right, you know that the velocity here is larger because you're adding positive velocity from the irrotational vortex, and the velocity there is lower. Right? Now, remember that for a potential flow, you can impose Bernoulli, and your constant is constant everywhere. This is very different from when we first discussed Bernoulli, where you can only assume that the constant was along a streamline, which means that you can directly deduce here that the pressure, because the velocity here is lower, the pressure is high. The pressure here is higher. Right? Bernoulli is P plus 1/2 of rho u squared. U is lower, so pressure is higher here. Pressure is lower here. So if I have a region of higher pressure on the bottom and lower pressure on the top, then I'm going to have a net force towards the upside. So I have a positive lift. Okay? So this is, this is it. Lift. So this is the fundamentals of how lift functions around an airfoil. Okay? So we'll discuss that. Maybe we'll do an example, but the problem is that as soon as you go away from a cylinder, all the analytics becomes really difficult. But you have to think around a wing. You have to imagine in your own mind that you're squeezing this cylinder to just a flat plate. And if there is no circulation around this flat plate, then there is no lift. Only if there is a net circulation around this flat plate, so if you integrate the velocity field along your flat plate or along your airfoil, if you get a net circulation, only then do you have lift. Right? So that's this is the flow around the cylinder. Now this example, you really have to know that. This is sort of a fundamental example in aerodynamics. All right, and now so the B was the lift force, and C, I'm just going to introduce two notations which you will find in many problems, and which just in aerodynamics and in anything you will find that often, and those are the pressure, the lift, and the drag coefficient. Pressure, lift, drag coefficient. Now, pressure, lift, and drag coefficients are the non-dimensionalized version of the drag force, the lift force, and the pressure. Now, if you think about the pressure, for instance, and remember that this is a high Reynolds number flow, in principle, because we're assuming it's inviscid, it's irrotational, therefore inviscid. If you wanted to non-dimensionalize pressure, what quantity would you use? You said something? Rho u squared. You would not use mu L u. Yeah, it's a typical inertial flow, so the scale for pressure will be rho u squared. What were you going to say?
Wouldn't it depend on the flow regime, or are we just going?
So the definition for the drag coefficient, usually, right, especially in aerodynamics, would be divided by rho u squared. Okay, that's just how it is. Now, you could also non-dimensionalize it. I think it's with mu times u divided by L, right? But that is if you have a viscous flow, then your force, you could non-dimensionalize your viscous force with that. But the number you would get, you would not call it a drag coefficient. Right? You get a non-dimensional drag, but really when you say drag coefficient, that's because you divide it by something which scales with rho u squared, and in fact you don't just scale it by rho u squared, you scale it with 1/2 of the rho u squared, and the 1/2 comes from the 1/2 in the Bernoulli equation. So pressure, so your pressure is often given or expressed in terms of the pressure coefficient. In terms of the pressure coefficient. A pressure coefficient is usually denoted by C, a capital C, and a small p. This is your pressure coefficient. And at any given point, it is equal to the pressure at this point minus the pressure at infinity divided by 1/2 rho u squared, where u is your velocity at infinity, your velocity, reference velocity. Okay? This is the pressure coefficient. And then for the lift coefficient and the drag coefficient, then, you just take, for the lift, coefficient and the drag coefficient, you call the lift coefficient capital C L, the drag coefficient capital C D, and the lift coefficient is going to be equal to L divided by 1/2 rho u squared times your frontal surface. So in this case, right, in our case, because we have a 2D flow, you can take S. S would be equal to 2 times the radius, right, the diameter. So it's the surface which is frontal to the to the incoming flow. So that's the reference surface, and the drag coefficient is the D divided by 1/2 rho u squared times your reference surface. This is how you would define your drag coefficient and your lift coefficient. Okay, so the last thing we'll discuss are the stagnation points and what happens to them, because that would also help you maybe to understand how lift is generated. Stagnation point and flow visualization. Why flow visualization? No, just stagnation point. So we're still looking at the flow around the cylinder. And so we'll discuss the stagnation points. And the stagnation points, they are formed, right? So the stagnation points are on the cylinder. Right? On the cylinder, we'll just discuss the regime where we have stagnation points on the cylinder. If you go to very large circulation, which I think experimentally you will never realize, you could have no stagnation point on the cylinder. We've seen that again, and then the stagnation point in the bulk of the flow. I'll do that later on the MATLAB, so you can see exactly how this works. But for now, we'll just assume, you'll see. So the stagnation points, we assume that they are formed on the cylinder. And for that, we're going to do everything in polar coordinates. So in polar coordinates on the cylinder, because of the no-slip boundary condition, we know that UR at r equals a theta is already equal to 0. Right? This is our no penetration boundary condition. The flow we have satisfies that. Right? So this is check. This is already the case. And so if we have a stagnation point, that means the velocity is equal to 0. So the only thing we need to look at is at the surface of the cylinder, make sure that the circumferential velocity is also equal to 0. Then we'll have a stagnation point. Yeah? So we'll simply look at the points on the cylinder, so the points at r equals a, so for which thetas is the circumferential equal to 0. Right? Now, how many solutions do we expect to this equation? From the flow that you saw, how many solutions do you expect? 2. Right? We expect that once we write this condition correctly, same thing. In an exam, always anticipate what you expect. So here, we're trying to find stagnation points. You kind of know there are 2. You know that the stagnation point equation is going to be given by the fact that the circumferential velocity is equal to 0, and you expect that you'll have 2 solutions, 2 thetas, which will tell you where your stagnation points are. Okay, so now this is no longer written, so I have to pull it out. Now let's just recall that for the flow around the cylinder, we had the following expression: u theta is equal to, it's written here, minus u times 1 plus a squared divided by r squared times sine of theta minus gamma divided by 2 pi r. That was our expression for u theta. And ur, I'm not going to rewrite ur, right? I'll just let you report it from your notes from Tuesday. Okay, so this is u theta. So our equation for the stagnation point, that implies, let me rewrite this equation here, and I have to replace r equals a, so I get minus, this is going to be equal to 1, so I have minus 2u sine theta minus gamma divided by 2 pi a equals to 0. That's the equation for my stagnation point. So minus 2 capital U sine theta minus gamma divided by 2 pi a equals to 0. So I need to find the solutions for that equation. Note that we are already on the right track, and we have an equation, and the only unknown in my equation is theta. In principle, once we graph everything, we'll see that, we only can have 2 solutions, or none. All right, so how can I write this? We'll write an equation for theta, and we'll write, how am I going to do that? Actually, I want it for gamma. So I'm going to rewrite this as gamma is going to be positive. Yeah. So I'm going to rewrite this as gamma is equal to minus 4 pi times a u sine theta. Okay. So this is the equation I have to solve. Now let me plot everything. So we're going to plot the function minus 5 pi au sine theta. Okay, so this is theta, and we're going to plot minus 4 pi au sine theta. So the function is going to be at first negative. That sign looks like that. this here is theta equals to pi. And this here is theta. So we only look at one period now. We don't need more than one period. Minus pi. Okay, this is my sine. And this here has a value of 4 pi AU. And that here has a value of minus 4 pi 8u. Okay, so you directly see that if my circulation is, let's talk only about positive circulation. Right? If we start having negative circulation, we just have the opposite picture. Right? With a lift force which is going to be downwards. Okay? So let's think about positive circulation. If my circulation is 0, where are my stagnation points? At 0 and at minus pi. That's what we had before. Right? We had one right at the at the front of the cylinder and one at the back. Yeah. Now, if I have a small circulation, right? So let me just plot that here. So let's say we have a small circulation here. Right. This is a non-zero gamma. So where is gamma equals to minus 4 pi AU squared? It's equal here and it's equal there. Yeah. So those are going to be the location of my two stagnation points. Right here and right there. And we can call them theta naught. So if you want to plot that, then on the circle, this is my circle here. Right, so this here corresponds to, so if I have an incoming flow here, I have two stagnation points at a small negative theta. So this stagnation point here is a small negative theta, so it's going to be here. Right, this angle here is going to be my first solution, and then the other solution is, well, the symmetric angle if you're starting from minus pi. So it's going to be this angle here. Right? My second stagnation point is going to be there. And so that means that I have streamlines leaving from those stagnation points. And so my flow is going to look like this. If I now plot streamlines, and the streamlines are going to look like that. On top, they're going to look like this. Okay. So that's the picture. If you have a positive circulation in the aerodynamic sense, and then you have a positive lift. Now, what happens when gamma takes on the value higher than 4 pi A times u? Do you have a solution? Huh? There is no more stagnation point. At least there is no more stagnation point on the cylinder. Exactly. There is no stagnation point on the cylinder. Actually, when we plot the flow, we'll see that there is a stagnation point in the flow. But here we only look at the cylinder. So once we reach the value of 4 pi AU, then there is no longer any stagnation points on the cylinder. So let me write this to summarize. When gamma, so the circulation is less than 4 pi times UA, then we have two stagnation points. Two stagnation points on the cylinder. And the coordinates is the solution of gamma equals minus 4 pi AU sine theta naught. And then when gamma is larger than 4 pi UA, then there is no stagnation point on the cylinder. Now the important thing to note here is that, as we discussed on Friday, for any circulation, value of the circulation, you have the flow around the cylinder. Right? So if I ask you to solve the flow around the cylinder, when we derived it, gamma was still unknown. It was still unfixed. You cannot fix the value of gamma for any kind of, for any gamma you can actually compute a solution to the potential flow around the cylinder. But what you see here is that once you fixed gamma, and let's say you fix gamma in this region, once you fix gamma, you fix the location of the stagnation point. Right? So you can think about gamma as fixing the location of your stagnation points, or conversely, if you fix the location of the stagnation points, then you fix gamma. And that's very important because this is at the basic of aerodynamics and what is called the cutter condition, right? So I'm going to try to show you that. Before I do this, let me show you the last MATLAB case where gamma is much larger than 4 pi a u. So if I did everything correctly, let's look at this. I have a uniform flow of strength 1, and this is it. So, and I have a radius. What is the radius of my cylinder? Oh, I haven't determined the radius of my cylinder. The radius of my cylinder is fixed by the dipole strength, so I don't know what it is. Okay, it doesn't matter. Let me just increase it randomly. Let me put it to 10. Let's see what happens. So it's still we still don't have we still have stagnation points. Note that the more, as we saw in the graph, the more I increase gamma, so I increase the circulation, you see that now my stagnation points have moved closer here. You see that? If I increase it more, they're going to move even closer here, and we're going to move closer here, and eventually I'm going to have no longer any stagnation point here. I'm just going to have a stagnation point which is going to start going into the bulk of the flow. So let me see for when this is going to happen. Let's move here to 15. So still increasing the circulation a little bit. And there you go. Okay, so now, once I go to 15 here, you see that now you have a stagnation point there. And you only see the streamlines, but you can get from the shape of the streamline that you have a stagnation point here. And what happens around is that you have sort of a pocket of air which is trapped and which keeps on circulating like this. So you have to think that there's so much viscosity that the cylinder was turning and there was sort of circulation, and now it's spinning so fast and the circulation is so high that the air which is in train around just loops around the cylinder. And so this is why you don't have a stagnation point at the surface of the cylinder. Yeah? Does that make sense? Okay. In that case, let me make a brief parallel with thin airfoil theory. And if we don't have the time to derive it fully in class, which I think we won't, I'll post a little clip where I show you the different steps of deriving the solution. Before we do that, we need to do complex potentials. So this is not until next week. So let me do a link with aerodynamics. So the flow around the cylinder, when there is no circulation, looks like this. Okay, and there is no lift. Okay. So you can directly do an analogy between the flow around the cylinder and the flow around a flat plate, and we take a flat plate as a proxy for an airfoil. So just think the cross section of a wing. And so if you have a flat plate here, right, then I'm actually exaggerating. Yeah, the streamlines don't even deviate, so you have just straight streamlines. Okay, and that is, in a way, this is not surprising because you have your own. Maybe when you were a kid, you like to stick your hand out of the window. Maybe your parents didn't let you. My parents did let me do that. They shouldn't have. When you have your hand flat, then you don't feel any lift force. Right? You just keep it like this straight. The flow flows on top. The flow flows on the bottom. You don't feel any force. Right? So this is here. You know there is no lift. Right? When you look at that, there is no circulation here. There is no lift, but this is not so surprising. You expect that there is no lift. Okay, now this is a plate with no incidence. You don't have an angle of attack. Now let's take a plate with an angle of attack. So now this is my plate, and this is my cylinder. Right? So this flow here, the flow around the cylinder with no circulation. This is flow around cylinder with zero, so with no circulation. This here is the same as the following flow. Right? Just think of this as your airfoil. If you wanted to have a flow with no circulation, actually I should do this in black because then you'll see the difference between the profile and the streamlines. And this here is in black. Same here and same here. Right, so the flow with no circulation around this airfoil would look like this. Okay? So if you computed a flow around a flat plate, inviscid flow, right, so we're assuming there's no effect of viscosity, so irrotational incompressible flow, and there was no circulation around your flat plate, then we get a flow like this. And on this plate here, there is no lift force. Right? Just like here, there's no circulation. Here, there is no circulation, and there is no lift force. And you can see it here. I mean, of course, you have a stagnation point there with high pressure, but you have the same stagnation point here with high pressure. Okay? And so in the end, when you integrate, everything cancels out, and you have no net lift force. Now, does that look like a reasonable flow to you? Now, what would you expect? Which part doesn't seem so good?
The one where the flow starts from the plate.
Where? Oh, this one, right?
Yeah.
So here, you don't expect the streamline to be attached there. Where do you expect it to be attached? At the trailing edge. Yeah. So you expect it to be at the trailing edge, and this is actually because you have a natural intuition for viscosity. Right? Even though we're assuming the flow is inviscid, in reality we know the flow is there is a certain amount of viscosity. So when the flow has now to move around this edge, it accelerates really quickly. That means that you have flow which goes to infinity at the edge, because it's accelerated here, right? But we know we have a no slip because there is a finite viscosity of air. So you have a lot of shear stress here, and the flow is going to be slowed down a lot, and that's going to pull this stagnation point. So the stagnation point towards the trailing edge, and it's going to be pinned at the trailing edge. Now, if you say that this is here unphysical, right, and you say no, I do not want this, I refuse, right, and you say the flow actually has to be attached, at least, if we have to model this as an inviscid flow, then we would have to attach this stagnation point at the trailing edge. Right, then the flow starts looking like that. Right? Doing this, imposing this condition, which is when you do that, you're adding some physics. This is called the Cotta condition. So this here is called the Cotta condition. This is called the kata condition, and when you impose the kata condition, then you do fix the value of the lift. Why? Because fixing this streamline to leave from the trailing edge, what it does in the equivalent circle, cylinder, is to fix the location of the stagnation point. Right? You're imposing, you're saying, well, I impose a kata condition, therefore I'm imposing the trailing edge, the stagnation point to be here, right? And this is the same as determining a position for the stagnation point on the cylinder, which fixes the location of which fixes the location of the stagnation point and therefore fixes the circulation. Okay, so that here is actually equivalent to fixing this location here. When you impose the kata condition, you essentially fixing the value of your stagnation of the location around your cylinder, right? So here, this kata condition is equivalent. It's equivalent to fixing the location of the stagnation point on a cylinder, right? And remember that fixing the location of the stagnation point on the cylinder is equivalent to fixing the circulation. So once you fixed the location of the stagnation point, you're fixing the circulation and you're fixing the value of the lift. Okay, so this is also equivalent to fixing the value of the circulation. So in a way, for a cylinder, you can have a solution to the flow for any value of the circulation, so you have an undetermined there. But if you now go to a real airfoil or to a flat plate, then by imposing the kata condition, you lift this unknown. If you fix the angle and you fix the location of this stagnation point, then you fix the value of the circulation and therefore of the lift. Okay, and actually the lift will be equal to the lift coefficient will be equal to 2 pi times alpha, the incidence angle. This is what you feel when you have your hand like this. If you put a small angle, then you feel a force lifting your hand up. Okay, I think we're done for the first hour. We're done also with the flow around the cylinder, and we'll discuss complex potential in the next hour. Okay, so we're gonna start again. So I am very sorry about the screen. It does look bad from where I am, but apparently this is nothing compared to how bad it looks from where you guys sit. So I will email again the people from the scheduling office. But I've emailed them a few times already over the past month. So I've asked for a new room already in September, and now I asked again. At some point, they have no choice. But perhaps somewhere in the campus there's a better room. So I think if you guys, organize yourself and write a nice little petition, then maybe I can just attach that to the email and just say this is actually really necessary. But I think I would need your help, because I've asked a few times, and it's not bad faith, but we're just the university is lacking space. So we're just scheduled at a time where all of the other classes, whether it's Instruxisal or they're all used. So it would have to be really somewhere else. So we'll have to ask. Okay, now someone asked about what it means for a cylinder to rotate. So I figured you should see this. So I don't know if any of you are aware of what that is. Maybe some in marine ship engineering. So this is a boat, and the propulsion is right here. That here is the propulsion, right? Those cylinders here are made to rotate with a motor. So you actually rotate the cylinder, and the rotation of the cylinder, because there is some viscosity in the air, not so much, but some, will drain the fluid around, And I saw another picture here, which is great, right? So imagine this is one of these posts which rotates. So if there is crosswind, right, then you have the exact, if this rotates, the rotation of the cylinder will create some circulation, a certain amount of circulation. And because then there will be circulation around the cylinder, there will be a lift. In that case, you just have to visually see that you have flow coming from this direction, and your circulation is positive in this direction. So it's the same configuration as the one we have in our example. So the lift is in this direction. Right? So this is a propulsion method, which is, believe it or not, actually used for ship. That is called the Magnus effect. So this Magnus has to do with rotation entraining some air, which means that in the end, when you compute, if you were measuring the flow velocity field and you were computing the circulation, you'll get a non-zero velocity field, a non-zero circulation. And if the thing is moving at the same time, then then you have a lift force generated. Okay, so we're going to go back to our lecture and we're going to discuss complex potentials. So this is number 5. Complex potentials, and this is still in chapter 7 of your book. It's chapter 7.4, I think. Right? And again, in your little concept map, complex potential is only associated with irrotational incompressible flows. Remember, when the flow is irrotational, it is by necessity inviscid. Yeah? So irrotational, inviscid flows. And now, on top of that, this is only valid if you have two-dimensional planar flows. So those are the same geometry as we are looking like here. We're assuming all the flow happens in the plane, and nothing changes in direction coming out of the board. So complex potentials, never use that, or even think about using that in any other situation than irrotational, incompressible, planar flow. For planar, two-dimensional flows. Now, this is a very fundamental topic, but this is always a difficult topic because in your engineering training, and it's not a bad thing, but you no longer see complex analysis. So complex potential used to be essentially it would be in aerodynamics there was 101. This is what you first studied because the methods of complex potentials allowed you to compute many flows very, very quickly. The thing is now we have computers that allow us to compute flows. We no longer really rely on analytical tricks to compute flows. And so, the topic of complex potential is sort of a little bit, it's a bit difficult because in a way, so what we're going to discuss here, we're not adding any concepts. Right? The flows which are described by complex potential are the exact same as what we discussed before, and if you wanted, you could do everything that you do with complex potentials with the real potentials which we used just in the previous lectures. Right? So we discussed potential flows. Nothing was complex in there. Everything was very real. You have imaginary numbers. Everything is real, and you can just use that if you want. There's no problem. But complex potentials make the whole analytics and the derivations much easier if you have background in complex analysis. Now most of you now don't, but if you sort of catch on the notations, it will still make your life easier. So it's still a topic which is taught, and it's also taught because for all of you which will do aerodynamics, to understand everything which I discussed about transforming the cylinder to a single plate, you need complex analysis to do that, and that gives you a lot of understanding, a lot of intuition for aerodynamics. So the way I'm going to so this part is a bit difficult. So remember, there are two things. Essentially, we're not introducing any new concepts. We are only introducing a new mathematical way of looking at things, right? So it's really just mathematical. It's no tricks, and I'll try to just introduce the notations. I won't describe any theory about complex analysis. But if you stay at the level of the notations, just take it for whatever it is. even if z is a complex number and not a real number, don't be afraid. Just differentiate and do everything like you know how to do. Then in principle, you can use complex analysis at the level that is required for this class. Okay? So with all of these, sort of, how do you call that? Disclaimers being done, I'll just go into complex potentials. So let's discuss number one, complex potentials. Okay, so at this point, remember we've discussed that we have an irrotational flow, and therefore our velocity derives from a potential. So we can write u as the gradient of a potential. This is a function here. This is the gradient. This is a real function, right? When I say real function, I don't mean that it's a fake function. I mean it's a function that takes its values in R, in the real. It's a number. Okay? But this is a real function. Okay, and it's a real function in the 2D plane. Now, even if you haven't had any background in complex analysis, you have seen complex numbers, right? This you have. And you know that a complex number is just another way of thinking about points. Okay, so we'll just remind you of that. So here, if I have a point, and this only works, complex potential only works if you're in the 2D plane. So we have a point. Our point has an x and a y coordinate. We can think about this point as an imaginary number. I'm always going to call the imaginary numbers a z, where z is equal to, the real part is going to be the x coordinate, and the imaginary part is going to be the y coordinate. Okay, so here z is a complex number, and x is the real part and y is the imaginary part. Now when I write my complex number in this way, I'm making a direct link between my Cartesian coordinate and the complex number. So this is another way of thinking about Cartesian coordinates. You can also write your point and locate it with polar coordinates, with an angle and the distance to the origin. Right? In that case, you know that z is equal, x in that case is equal to r cosine theta plus I times r sine theta. And this is x, this is y. And another way of representing this number is by its modulus, so the distance to the origin r, exponential I times the argument theta. Right? So we'll use complex number in that context. Right? So the complex number z will represent the location in the 2D plane. The real position is the x position, the imaginary part is the y position. Or if you write it in terms of complex exponentials, right, then the modulus is going to be r, and the argument, the angle, is going to be, well, the polar angle theta. Okay, and so what we're going to do is to define also, associate with that, instead of having a real potential depending on x and y, we'll have a complex potential as a function of the complex variable z. Right? And so we can define a complex potential at every single point, which we represent with the complex variable. So let me write that. So the potential that we've seen can be generalized to complex potentials. Okay? And so my complex potential usually is represented with the letter W. So now I have W as a function of z. W here is my complex potential. And Z is the complex variable. It's just the location where you're looking at the pressure or the velocity. It's just the location in the plane. This is your complex variable, which is just, you know, another way of thinking about the position vector x. Now my complex potential is a complex number, so it has a real part and an imaginary part. So if I decompose, I'm going to call phi the real part, plus I times C Z. So phi is the real part, psi is the imaginary part. And now this is no coincidence, right? So I define my complex potential such that the real part of my function is actually the same potential as the one we've discussed before. Okay, so this phi here is the velocity potential. Okay? So if instead of writing phi as a function of z, you know, I can write phi as a function of z, really phi here is a function of x plus iy. So you could think about phi as a function of x and y, and if you took the gradient of this function, you would have exactly the velocity field. Okay, so this phi, the real part, is the potential. Now don't ask me why, it just happens that, I mean, to be honest, I don't really care too much as to why. Mathematically, it so happens that the imaginary part is the stream function. That's why you call it psi. We already introduced the stream function. It so happens that the imaginary part in that case would be the stream function. Right? And if you wonder why, it's just mathematics. If you just write the formulas, everything, it turns out that this is what it is. Okay, so you can generalize your potential to get a complex potential. Your complex potential has a real part and has an imaginary part. The real part is your velocity potential, and your imaginary part is the stream function. So for example, let me give you an example of complex potential. Right? How a complex potential would look like. A complex potential could be simply just a function of z. Right? So the simplest function of z you can imagine is just, for instance, z to the power n. N being 1, 2, 3, 1/2. Right? N could be equal to 1/2, to 1, or to 2, to any number. Okay? This is a function of the variable z, and that will represent a particular potential. All right? This is how a complex function looks like. You know real functions, so functions of x or functions of y, you know, of real numbers. Or you have functions of complex numbers, which are functions of z's, right? And this is x plus y plus iy. So there's nothing really, terrifying about that. It's just a new object, which is a function of the complex variable. All right. So now this is number A. This is A potential. Now, of course, because the real part is the same as the potential we had before, there is a link between the complex potential and the velocity field. Right? Remember that if you have the potential, you take the gradient, right? And you have the velocity field. For complex potential, it is similar, but actually it is easier. And that's why actually people use complex potential, because then you don't have to worry about partial derivatives. You just take derivatives of the complex variable. So it so happens that, what do you think the equivalent version of a gradient would be? It would just be the derivative with respect to z. Right? So if you take your complex potential and you differentiate with respect to z, right? This here is going to be linked to the velocity. But now it's not exactly going to be the velocity. This is the one thing which is strange. The real part of this derivative is going to be the x component of the velocity, and the only thing you have to always worry about is the imaginary part, because the imaginary part of the derivative is going to be minus the y component of the velocity. And again, if you ask why, it's simply the mathematics. That's how the mathematics works out, right? But the good thing is, so this, let me write that. So that means here we can take the gradient. It's not really a gradient, it's a derivative of W, of the complex potential, to get to the velocity. So here is a very important formula. If you differentiate with respect to the complex variable your complex potential, you get something which is associated to the velocity. Now this minus sign might be a hassle to remember, but if you want, the good thing is, if I take the same example as what I had before, and we'll see just a minute what flow this corresponds to, then, right, so say I have a flow represented by this complex potential, and I want to get to the velocity. What is the velocity field? Well, you simply differentiate your function with respect to z. Right? And the whole point of complex functions is that they just look like the functions you know. So they just differentiate the same way. Right? Even though this is a new object, what would be your intuition for what this derivative is? N times z to the n minus 1. And this is exactly what it is. So for all the functions that we will use in this class, except there's a problem when theta goes from more than 0 to 2 pi, so when you loop around, then you might have some problems, but we will never discuss that. Don't worry. So for all of the rest, everything which you know for real functions still holds for complex functions. So if you want to compute the derivative, it's just n times z to the power n minus 1. Okay, so the algebra is very easy for complex potentials. You don't even have to compute the gradient, you just take the derivatives, but then you have to be able to take the real part and the imaginary part. Okay, so this is complex potential. What did I do? Number 1 was complex potentials, okay, and number 2, we'll just rewrite everything that we've done before, but with the terminology of complex potentials. So let's do that. So this is 2. Complex potential of our important flows. Complex potentials of our, we call them the building blocks, remember? Of our building blocks. So if you want to use complex potentials, and I encourage, of course, it's a new mathematical object, and again, any problems that you will be giving in this class, you should be able to do it with just regular potentials or complex potentials. But once you're used to complex potentials, you're much less likely to make a calculation mistake if you use complex potentials. They're just easier. To play with, but if you're uncomfortable with them, then you don't have to use them. Okay, so let's say that we have so what is a uniform flow? In complex potentials, the way you will represent a uniform flow is the following. So say we're representing this uniform flow here, right? And it has component u and v. Another way to represent this flow is to say that it has a magnitude u and it has an angle, right, phi. So let me just say that this is magnitude u and this angle here is phi, and the angle is the angle at which your uniform flow is. Right. So then for this flow, the complex potential is just Wz is equal to u exponential minus I phi times the complex variable z. That's the first complex potential you need to know. Right? Now, of course, this is the only one you need to know, but this is also the only one which is awkward because it has to do with velocity. Yeah? So, of course, if you were to represent this with a complex potential, you would want to say this is just u times the position vector. So you would expect a plus here. Right? But it's a minus, and we'll just see why in a second. Right, so if you want to go back to the velocity field, what do? You take the derivative. So if you want to go to u minus iv, this is dwz divided by dz. Okay? Now my wz for a uniform flow is just u exponential minus I phi times z. So what is the derivative of this? Right? Capital U is a constant, phi is a constant, so what's the derivative of this function here? Remember, everything works just like our regular functions, so what is the derivative of this function? It's just u e to the minus I phi. Yeah? So the dz over dz is just 1, so this is u. Sorry, there is no bar here. Oh, there is, but there's the magnitude. U e to the minus I phi, right? So this is your velocity. Now, if I write it, this is u cosine phi minus I times u sine phi, right? So you see here that u I should put it right here. You see that this here, u cosine phi, is the x component, right? And u sine phi is the v component. Right? So when you take the real and imaginary part of that, you do have the real part, which is just u, and the imaginary part of that is minus v. Right? So it's minus v. So this here is v, which is what you expect. Yeah? Is that clear? So this is the only part where you have to be careful. Always remember that when you take the gradient of your complex potential, and when you differentiate with respect to z, your complex potential, the function you get, the real part, is always going to be the x component of your velocity field, but the imaginary part will be minus the y component. That's the only thing you always have to be worried about. You have to be careful, not worried. You have to be careful about this. Okay, so this is for your uniform flow. Now, let's look at sources and sink. So sources and sink look just like our other sources and sinks. So if this is QS, I think I called it capital, I forgot. Did I call it capital Q in the previous lecture, or QS? I think it was capital Q, Okay, so we have a source of volumetric flow rate capital Q, right? And then in that case, the complex potential is looks exactly like the one for the real potential, and it's going to be Q divided by 2 pi times the natural log of z. Now again, you haven't seen much of complex analysis, but the natural log of a complex number behaves just the same way as the natural log as real numbers. Right? So even if you haven't seen that, you've never seen a mathematical definition for that, but you can still use it. And just so you're confident that you can do it, let's look a little bit how you would play with that. So if you were to if you wanted to look at the potential and the stream function, so let's go back to this. So remember, this is just so you're fully comfortable with that. All right. Remember that my complex potential, the real part, is my potential, and the imaginary part is my stream function, in principle. So how does that play out? Now let's take the real part of our complex potential. So omega z is equal to q divided by 2 pi log of z. And I'm going to represent z now with the polar coordinates. Okay? So I'm going to write z as r exponential I theta. Okay? Then this is the log of a complex function, but it behaves just the same way as it satisfies all of the rules which you already know for the natural logarithm. So this is the same as the logarithm of r plus the logarithm of e I theta. Now what do you think the logarithm of e I theta is? I theta. Yeah? So this is where you might run into some troubles, right? And we'll never discuss that. You know, you will have some troubles when theta goes from, theta goes from 0 to 2 pi, and then it goes above 2 pi, then you have a different value for your complex part, but it doesn't look like a function anymore. So this is when you have problems, we'll never discuss that. Just note, do you remember that this here, so q, the real part, so the real part of wz is indeed q divided by 2 pi times log of r. Does that correspond to the definition we have for the real potential? Yes, right? Remember? This is really the same as for the real potential. And if you look at the imaginary part, well, we've never computed the stream function for a source, but you can do it. Right? Remember stream functions from, I think, the third or the fourth lectures, we computed stream functions. So I encourage you just to take the velocity field. And from the velocity field, you can compute the stream function. And when you compute the stream function, you should get to what we have here, which is the imaginary part of this, which is q divided by 2 pi times theta. Now, you haven't computed the stream functions, but you see that this is a stream function. Right? Remember, the stream function is the function such that the contours are streamlines. Now, what are streamlines? What are streamlines of our source? Huh? Yeah, the radii, like radii are stream function, are streamlines. This here is a streamline, right? Those are the streamlines of our source. Now look, my stream function. When is my stream function equal to a constant? It's equal to a constant when theta is equal to a constant. And in polar coordinate, theta equals to a constant is an equation for exactly a radii. Yeah? So this is okay. Now, if you wanted to get to the velocity field, you would do the same thing. You would compute dw z over dz. Right? I'm not going to do it. You can compute that, and you'll see you have the velocity field that we computed before for a source, except you have to be careful that the imaginary part is minus the y component. Eh? Always be careful about that. So sources and sinks. Let's continue and introduce irrotational vortices. See, irrotational vortex. So for an irrotational vortex, then the complex potential again looks very much like like what we had before. Now it's going to be minus I times gamma divided by 2 pi log of z. This is the complex potential for an irrotational vortex. All right, so now we can do the same, just to convince you that you've already seen that. So let's look at the real part and the imaginary part. So my complex potential is minus I times gamma. Now, I have to say here, when I write minus gamma, I am back to our previous notation. Yeah? I'm back to the notation where gamma is positive in this direction. So I'm consistent with the notation that we had before we did the example on the cylinder where gamma was positive in the other direction. That's the only part where we make the link with aerodynamics. So this is the only part where I put a minus sign. And here we're back to the same notation as before. So I gamma divided by 2 pi log of r exponential I theta. All right, so here again we're going to have minus I gamma divided by 2 pi log of r plus I theta. Right, so I'm not going to discuss the potential. So you see the potential is going to be gamma theta divided by 2 pi. And your stream function is minus gamma times 2 pi log of r. Now, does that stream function here make sense? Yes. Right? Remember, the stream function is such that your streamlines are contours of the stream functions. So when is this function here equal to a constant? When r is equal to a constant. Right? When you are in a circle. Now, circles are streamlines for rotational vortices. Yeah. So the good thing with complex potential is that you have the potential, the complex. You have the potential, velocity potential, the stream functions, and if you just differentiate the velocity fields, and they are all in a very nice, well, nice. It depends on who you ask, but in a compact notation. Okay, and the last one is the dipole. Okay, this is all going very. Time is flying. D is the dipole. And Wz is equal to D. Well, D can be a complex number that characterizes your dipolar strength divided by 2 pi z. Okay, so this is for your dipole. Okay, now, what I'm going to do now is just a list of examples, okay, just to show you how you can use that to your advantage, you know, how it's relatively easy to use. And so we'll do several examples, but I think, given that I just have 10 minutes, I'll do the easiest one first. And then on Friday, we'll redo the flow around the cylinder. And then we'll do flow in corners, and if we have time we'll do flow around the plate, but I'm not sure we will have time. We'll see. Yeah, I think the best is we'll just do examples. Okay, so 3. Examples, and the first one we'll do is one which we've already had this example, but we'll see it in a bit different setting. The rotational vortex close to a wall. Right? Again, if you have to look at the motion of an irrotational vortex close to the wall, or in your homework, I think you have the irrotational vortex with another irrotational vortex which is counterclockwise, or you have a irrotational vortex interacting with another irrotational vortex which are moving in the same direction. So you can always do use the real potentials or just use the velocity fields, right? But now on top of that, if you want to solve those problems, you can use complex potentials, and if once you're familiar with them, they will make the algebra easier. So let's assume this is my wall, right? And let's say I'm just going to at this point put my reference at the center of my wall here. So this is x this is y, and let's say at coordinate x0, 0, let's assume I have an irrotational vortex, and let's say my irrotational vortex has a positive circulation in the sense of the non-aerodynamics notation, so this is positive now, and let's think about how it moves. Now, remember, I'll just write it, but what we discussed, I think actually in lecture we did something slightly different. We discussed one vortex here with another vortex here of opposite direction, right? But this is actually how you would represent the wall. So let's say that you had a problem and they ask you to represent the flow induced around a point vortex. So you have an infinite amount of vorticity stuck here, and you're wondering what's going to happen to this vortex, right? Is it going to stay here or is it going to move? As you will see, it actually has to move. But how would you make sure that you have an implicit flow where you model the fact that you have an irrotational vortex here and that you have a wall here? So if you have to model this, then of course the first thing, if you have to say, well, we have a vortex at this location, is you put an irrotational vortex at this point. You put an irrotational vortex at this point. What is the flow at infinity? Well, there is no flow at infinity, so you would not add a uniform flow. Right? It wouldn't make sense at this point if you're just representing a single, just like imagine you had this, you just generated a smoke ring, and there's like, at some point you can think of this as a line vortex, and it's interacting with the wall. There is no flow at infinity, so you have no flow in infinity. Now, in this entire region here, to the right of the wall, would it make sense to add any other of our little building blocks? No, right? Because there's nothing. We're not assuming there to be anything. We're just assuming that we have a lot of vorticity right at this point. Right? So anywhere here to represent this side, we're done. We're set. Right? But if we just leave it as that, do we satisfy the right boundary condition here? Now, what boundary condition do we have to satisfy here? No penetration. Right? Now, of course, what you do know that the flow has, if you think about the streamlines, your streamlines look like this. Right? So in particular, say at this point, for instance, my flow, my irrotational vortex generates a flow into the wall. Right? And out of here, if I'm thinking about this location here, my irrotational vortex generates a flow which is coming out of the wall. So we don't satisfy the no penetration boundary condition. Now, how could we satisfy the no penetration boundary condition? So we already had that, and you could do that by just putting a mirror image of your vortex here. Now, because this is a wall, you can put whatever you want here, right? The flow, and the flow is going to be infinity here, but you can put stuff here just to make sure you model an irrotational that you model here at that here a wall. You have a no penetration boundary condition, right? So the trick is to put right there the image vortex of circulation minus gamma, because this one will generate the right velocity at this point in this direction, right? And this negative x component will cancel this positive x component, and so your velocity field then will be in the direction of the wall, which is fine. Because our flow, we are assuming our flow to be irrotational, therefore implicit, and therefore there can be a slip boundary condition. You can have a non-zero boundary at the wall, provided that it's only in tangential direction, right? So when I add those two, I get that, right? But that is okay, because it's fine. It's in the wall, and I'll have the same here. I'll have a velocity here. Okay, so this is how you would construct it. Now let's briefly do it analytically and use complex potentials. Right. So let's look at the system. So we're putting 1 plus gamma at location x0, 0. And we're putting 1 negative gamma at the location minus x0, not 0. Let's make sure that we satisfy the no slip boundary condition. So is that really what we want to represent? So how would I compute my complex potential? Well, my complex potential would just be the sum of the complex potential generated by each vortex, right? So the vortex on the right has circulation gamma, and it's at x naught. So the complex potential associated is minus I gamma divided by 2 pi log of z, but it's actually log of z if the vortex is at the origin. Here my vortex is not at the origin, so I have to take minus the complex number associated with this location here. Right? So you can call it z naught or x naught. You know, z naught is equal to x0 plus 0 times I. Yeah? So I can call it just x naught or z naught, it doesn't really matter. Let me just put x naught. And the complex potential associated with the left-hand side vortex is, so the circulation is now minus gamma. So it's minus I times minus gamma, so it's plus I gamma divided by 2 pi log of z minus x naught, so it's plus x naught. This is my complex potentials. If I want to get to my velocity, I know that u minus iv is equal to d wz dz. So I just have to differentiate this. Now how do I do that? You just use the same rules as what you know already for real functions. So what is the derivative of log of z minus x naught? It's 1 over z minus x naught, the same as what you're used to. Okay, so this is 1 divided by z minus x naught, and this is going to be plus I gamma divided by 2 pi times 1 divided by z plus x naught. Okay? So, does this satisfy the no penetration boundary condition at the wall? Right? That will be the case if, so we have to be at the wall. Okay, so let's think about, so at the wall z is equal to, so x is equal to 0. Our wall is at x equals to 0, and therefore z is equal to I times y. We have no real part. Yeah? Yes?
Yeah.
So this is my wall. At my wall, let's see what my velocity field is at the wall. So u minus iv, let me put here as a shortcut at the wall, is going to be equal to minus I times gamma divided by 2 pi. Actually, let me simplify this expression first. And then we'll do so. I'm just going to add a line here where I simplify that. I'm going to put everything under the same denominator. All right, so to do that, you know how to do that. So let me just write it. So it's minus I gamma divided by 2 pi. So I have this term here. So I have a z plus x naught minus z minus x naught. So it's a plus x naught divided by z minus x naught times z plus x naught. Right? So in the end you have minus I gamma divided by 2 pi times 2 x naught z squared minus x naught squared. So when I'm just going to move that down here. So when I am at the wall, then I have minus I gamma divided by 2 pi 2 x naught divided by z squared. Now at the wall, z squared is just iy. So what is iy squared? It's minus y squared. Yeah, I squared is minus 1. This is what you have to remember with complex numbers. Yeah? So when I take z squared at the wall, it's minus y squared. So I have minus y squared minus x naught squared. Right? And we are not. So if I just rewrite it, this is I gamma x naught divided by pi y squared plus x0 squared. This is my velocity field at the boundary. Now, do I satisfy my no penetration boundary condition? The answer is yes. But the real question is like, how do you see that you actually satisfy the no penetration boundary condition?
The real part is 0.
Yeah, exactly. The real part, so where is the real part? It's not there. Right? The real part, is 0, and I only have an imaginary part. So I know the velocity at the wall is in the v direction. Now the one thing you have to be careful is the sign. Right? So which sign does v have? Negative, right? Because this here is negative v. So v is negative now, and if you look at your picture, you actually knew that v was negative from the picture, right? So you expected a negative number. Yeah? Now we're done, but let me ask you, given this, is there a net force on the wall? Does the rotational vortex exert a net force on the wall? So who says the rotational vortex exerts a net force on the wall? And who says it exerts no net force on the wall? Okay, a lot of undecided people. What would you have to compute to know whether it exerts a force on the wall or not?
The pressure.
So let's be very specific. What exactly would you compute? What exactly would you compute? Which number would you write? So let's force. You're on the right track, eh? But what would you write? It's important because sometimes in an exam, you sort of have vague concepts, but it's not precise. What formula do you write? So what would you write? You would write what? The force on the wall is equal to what?
The integral of pressure.
Integral from where to where?
Minus infinity to
Yeah, from y equals to minus infinity to plus infinity of what?
the pressure.
Pressure or? No. Shear stress, please. No shear stress if we're in viscid flows, right? No, it's minus the pressure. Right? Minus the pressure. But then it really depends which direction, times your normal vector. And the normal the vector in that case is pointing in the x direction. So minus p times x times
The area.
yeah, the area. In that case, how would you write the area? dy.
dy.
Yeah, this is just dy. And how do you get to the pressure? From unsteady Bernoulli, but yeah, in that case, you don't have, well, if the strength of your potential doesn't change, or if you're following the value of your thing, yeah, you're right. Actually, it's the unsteady Bernoulli equation. Yeah, okay. But you need to be able to write this integral here. Huh? And this is just a simplified version of that, right? This is this, but you know that it has two terms inside, and you know that because there is it's inviscid, there will be no net contribution of that component. Yeah. Okay, good. I'll see you on Friday, and I'm going to stop this recording.